Okay, let's start the lesson. So last week we discussed about physical quantities. So if I summarize what we learned last week, so we first discuss about what is a physical quantity. So if you can remember, a physical quantity is something that you can measure. So that's what we actually discussed. So after that we discussed about 7 fundamental quantities, if you can remember. So with their basic unit, we discussed about that one, and we identified 7 such fundamental units. So I said that you need to remember throughout your period of study that these 7 units, because we are using these 7 fundamental quantities to derive other physical quantities. So we discussed about few derived physical quantities like force, volume, area. Like that way, by using these fundamental 7 quantities, we derived some other physical quantities. We call them derived physical quantities, right? After that one, we try to find the units of some derived quantities, right? We look at density, we look at acceleration, momentum. Like that way, we had a whole list of physical quantities and we tried to find the units. There we learned about some special units also, basically like Newton, Pascal, Joule. Like that way we identified that there are some special standard units. After that we discussed about two supplementary units about the plane angle and solid angle, steradian and radian. Then we look at how to convert the units, right? We did some examples on how to convert millimeters to meters, kilometers to meters, like that way, by using the meaning of prefixes. So we talk about from 10 to the power 18 to minus 10 to the power 18. We discuss what are the prefixes used and how to convert the units. So we discussed this part. After that, actually we went to the basic maths part. Then there we discuss about some how to find area, how to find volume, and what are the basic algebra expressions that we need to know as A-level students. And then we go to trigonometry and we discuss that big table, and I asked you to remember that one for your entire life, that you may have to use that one. So like that way we did some examples also. I gave you few homeworks also. So I hope that you have completed the homework. If you have completed, please send me the answers through WhatsApp, and few of you have actually sent the answers, and very good. So those who have sent, they have done well. There were small mistakes, but I personally guided them how to get that corrected. So if you haven't done them, please do, and please send me the answers so I can guide you what are the wrong things and what are the correct things that you have to do, right? So from today onwards, I am going to start the new section of the chapter. So it is called the dimensional analysis. Dimensions and dimensional analysis. So students, please write down the topic: dimensions and dimensional analysis. So this is a very interesting part that you will learn under this first unit. Okay, so this is the place where that you are starting to actually do physics, right? We are going to do some interesting, very interesting questions from the dimensional analysis, right? So the question first comes is, what do you mean by a dimension? So actually dimensions are also something like units that scientists have agreed to use to represent physical quantities in terms of fundamental physical quantities. So if I tell like that way, it is just a symbolic expression. Now we know in physics as well as in maths, we like to use symbols rather than words, right? So if you can remember the last week, we write that if you say density equals mass divided by volume, right? So this is actually writing a lot of things. So actually in physics as well as in maths, we prefer to use symbols rather than writing the whole word. So actually we can write this equation in a symbolic form, right? So if you write the density, usually we use rho as the symbol of density, mass we use symbol M, volume as capital V. Though these are some usually using symbols. But if you write this symbol, it doesn't say how this one is connected to your fundamental quantities. Now I said you, we have 7 fundamental quantities and each of the other derived quantities are coming from the fundamental quantities. By adding, by multiplying, by dividing the fundamental quantities, you can take any physical quantity. Now if you write in this format, you cannot understand how this one is related to the fundamental quantity. Right? You can see here mass is actually a fundamental quantity, so you can relate that one. But if you go to volume, there's no any definite relationship that you can say, that you can see here, that how it is connected to the fundamental quantities. So scientists have identified, or they have introduced a new method called dimensions, and the dimensions are simply a symbolic format. It's a symbolic format to show how fundamental physical quantities are related to other physical quantities. So this is what we call the dimension, right? So you can start writing down, write down like that way. Dimensions are the symbolic format. Dimensions are the symbolic format that is used to represent the relationship between symbolic format that is used to represent the relationship between fundamental physical quantities, and other derived physical quantities, right? So this, what is the symbolic format? So for that one also scientists have agreed a symbolic format like this way. So under our A-level syllabus, we actually have to consider only 3 fundamental dimensions only, but for all the 7 fundamental quantities, they have defined 7 symbols, right? They have defined 7 separate symbols, but under our A-level syllabus, we only have to consider 3 of them, right? So we know that we have a fundamental quantity called mass. So they are saying you have to use capital M as the symbol of mass. That means if you have any mass, then you can represent that mass by the symbol capital M. And we have another important physical quantity which is called length. So they are asked us to use capital L as the symbol of any kind of length, right? It can be kilometers, it can be in meters, any length you can represent by using symbol capital L. Then the other fundamental quantity that they have taken is time. So they have asked us to use capital T as the fundamental dimension or the symbolic format of time as capital T. So we call this MLT system. Okay, so in under A levels we are going to learn about how to use this MLT system in real life applications. So there are for other physical quantities like thermodynamic temperature or the absolute temperature, you have a symbol called theta. Like that way you have other symbols, right? But in physics of A level syllabus, we only have to go through these 3 basic symbols. Other than these symbols, we will not get questions. if they are going to give a question, then they will give, use this one as the dimension of this one. Like that way they will give. We will do some examples, right? Then you will understand what kind of questions that they are going to ask from you with this lesson. Okay, so now you can write down under the scope that we have to learn. Write down under the scope that we have to learn. Under the scope that we have to learn, we have three fundamental dimensions. We have three fundamental dimensions. We have three fundamental dimensions. They are, you can put a semicolon, they are mass, capital M, length, capital L, time, capital T. Right. Now let's see how to use these MLT symbols in questions. Right. Okay. Now let's start from the beginning. So in the derived physical quantity list, we learned something called, first one is area. Right. We learned about area. So we represented area as length multiplied by width, right? This is the definition of area. I am starting from the very basic one. So if you write down in the symbolic format, area equals A and length L and width W. Now if you need to relate this area into the fundamental quantities, now we can do something like this. So now I am going to find the dimensions of area. Dimensions of area. So dimensions of area means it is the symbolic format how this area is related to our fundamental quantities. That is what we call as finding the dimensions of area. Again I will repeat, finding the dimensions of area means we are going to find the relationship between fundamental quantities and area. That is what we are going to do. So in physics, the standard is, if you are going to find the dimension of any physical quantity, you can represent that one by using a square bracket. So if you put something like this, if you put a square bracket to any physical component, physical quantity, this represents finding dimensions. This represents finding dimensions, right? So this one actually says to the viewer or the who is looking at your paper or the book. So this symbol says, okay, now I am going to find the dimensions of area. That is the meaning of this square bracket, right? So if you put the square bracket to your left hand side, then you have to put the square bracket to your right hand side. Now the dimensions, this bracket you can separate. You can take the dimensions of each term separately. So you can take the dimension of length separately and dimensions of width separately. So this is the meaning of that one. So if you need to find the dimensions of area, then we have to take the dimensions of LW. So you can break that one into two parts like this way, right? You can separately take the dimensions of L multiplied by dimensions of W. Now we know that length is a length. No? So what was the symbol that we used was capital L. So dimension of capital L we can write as simple L as capital L. Again width. Width is also a length. No? So if you take a square or rectangle, this is the length, this is the width. It is also a length. So you can put capital L here. Now L into L means L square, L to the power 2. So the dimension of area is written as L square. Dimension of area is written as L square. So this analysis, the finding this or this simplification is called the finding dimensions, right? And on the one part of dimensional analysis. This is part of dimensional analysis, right? I hope this is very clear to you, right? Okay, you can quickly write this down. Then we can go to a better example, right? Please take this one. Okay, right, good. Now we will go quickly, okay? Now I will write down the physical quantity. Then you have to write down the definition and we have to quickly find the dimensions. And so these are not difficult, these are the things that we already discussed last week, okay? So if you go to area of volume, quickly write down the expression that will be length into width into height. Now quickly find the dimensions. So the dimensions of volume. So please put this square bracket. That is a must. Okay. Don't forget that mark. It is essential. Equals L. You can separate and put. Okay. No need to put the whole thing and then separate. You can put separately at once. That is no issue, right? Length, dimensions of width, and dimensions of height. So dimension of length is capital L, dimension of width is capital L, dimension of height is capital L. Therefore, the dimension of volume is L to the power 3. Simple. So if you go to another one, we will say density rho is equal to mass divided by volume. Rho is equal to mass divided by volume. Now quickly find the dimensions of density quickly. So first thing is that you have to put the curl bracket here. Rho equals dimensions of mass divided by dimensions of volume. Now you already know dimension of mass is capital M. Dimension of volume is L to the power 3. Then if you take this one to the top side, that will become L minus 3. Right? So what happens is it becomes M L minus 3. So this is the dimension of density. It is very simple like that. Right. So you go to the next one. So you can write down with me. Right? That is for density. Then if you go to, we will go to the velocity. So velocity we write as displacement divided by time taken. So if you take the dimensions of velocity, you have to put the square bracket like this and put the square bracket like this and put the square bracket for time like this. Now dimensions of velocity is equal to the dimension of the distance. It is called L because distance is also a length, type of length. So you can put capital L here and time capital T here. Now you know when you take this one to the top side, your power becomes minus. So it will become LT minus 1. So this is the dimension of velocity. I will erase this one. So next we can find the dimension of acceleration. If you can remember the definition, what is the definition of acceleration? Velocity divided by time taken. Please tell me if I am going too fast, please let me know through the chat. So I will slow down, okay? But these are very simple things, that's why I am going bit fast. Now if I apply for the acceleration, you can put the dimension mark like this, then for velocity, and then for time. So now the dimension of velocity you have already calculated. The first one, that is L t minus 1 divided by t. Now you can take this t to the top, then it will give you L t minus 1 t minus 1. Now if you can remember the all-level simplification of indices, when you have the same base, the two indices you can add together. So it will give you Lt minus 2. So this is the dimension of acceleration, Lt minus 2. Right. Then if you go to the next, as I can remember, the next physical quantity was momentum, right? So the momentum equation was momentum, if I take momentum as T, mass into velocity. So this is the dimension, mass, this is the equation of momentum. Then if you need to find the dimensions of momentum, put the square bracket, mass into volume. So you can write down mass, velocity is Lt minus 1. So you can easily calculate the dimension of momentum. Then if I go to force, so we know the equation of force. Force is equal to mass into acceleration. So you can put the dimension mark, take in the dimensions, mass into acceleration, then dimensions of force equals m, acceleration is Lt minus 2. So the dimensions of force is mLt minus 2. Then if you go to the next physical quantity, I will take pressure, capital P. So the pressure is equal to force divided by area. So you have to take the dimensions, capital P dimension equal capital F dimension divided by capital A dimension. Now you already have calculated the dimension of capital F. That will be m L t minus 2 divided by L to the power 2, right? Because area has the dimensions of L square, right? Now you can simplify 1 L square, L here and one of the L in here will be getting cancelled out. Therefore, you can take this one to the top side, then it will also become L minus 1 and T minus 2 is remaining like that. Therefore, the dimensions of pressure will be mL minus 1 T minus 2. Okay, what are the other physical quantities that we discussed? We discussed work, right? Energy and work also we discussed. So if you go to energy, energy equals mass into speed or the velocity square. Mass into velocity square. This is the famous equation of Albert Einstein. So you can use this one to find the dimensions of energy. So dimensions of energy equal dimensions of mass. Now you have c square, right? C means actually velocity of light. So you can put like this. You can put the dimension of c and then you can take the square of it, right? Because this dimension is only possible for a physical quantity. So c is the physical quantity here. So you can take the dimension of physical quantity and then you can take the square of it. Now you can substitute here. Mass dimension is capital M. C means speed or velocity, no? The dimension of velocity was Lt minus 1. Now you have to take the square of the total. Now we have to take the square of the total. please be careful when we are writing this one. So some students, what they do is they just write down LT minus 1 and they just put square here. So without putting any bracket, then what happens is someone can mistaken and put only the next step MLT minus 2 only. That is completely wrong. Therefore, keep in mind you have to put a bracket here. Right? Put a bracket here, then you will understand that this 2 is belong to both L as well as T. Now when we expand this expression, what you can get is ml square T minus 2. So the dimension of energy is ml square T minus 2. Right? Okay. Next, if you go to the work, W, we discuss this equation, W equals force into displacement. Now you can take the dimensions of work equal dimension of force multiplied by dimension of the distance or the displacement. So force we have already calculated, if you can remember, ml T minus 2. Right? I can remember this because I have practiced this one for a long time, so I can remember. Right? But and you will also get that what you call proficiency, like in Sinhala or like in English you have proficient, no? You can talk anywhere, no? So like that when you do this one for some time, then you will automatically get the proficiency in this one, right? So this one is MLL means ml squared T minus 2. So we actually discussed this one previous week also, that energy and work will have the same units, right? If you can remember, we got the same unit. Like that way, here you have get the same dimensions. That is why we call it actually that energy and work are actually similar things, right? Okay. So these are the basic things that we need to know regarding the dimensions. These are the basic derived physical quantities, right? That means most frequently used derived physical quantities are these physical quantities. If you have any other physical quantity discussed last week, please tell me, then I can find the dimension of that one also, right? So please take this down, right? Okay, before going to the next few examples, you should be very clear on this. If you have any question regarding this, please drop a message, or you can raise hand and talk. Right. Since there are no questions, then we can move to the next part of the lesson. Now, what is the purpose of finding this one, right? Why people need these dimensions and why people need these physical quantities? What is the purpose of writing this thing? What is the meaning of getting the relationship between fundamental physical quantity and other physical quantity? What is the reason? So the thing is, we actually in A-level physics, we do not have much use of this one. We do not have much use here. But when you are going for a higher education on physics, then there are things like you have to model something, right? That means if you need to make a bridge or a dam like thing, then before you are constructing the real one, then you have to first construct a model of that one. So when you are constructing the model, you have to take the bigger one and shrink that one, right? That means you have to build exactly the same one, but in a small size. That's how actually those vehicles, aeroplanes and everything is being designed in practically. So what we do is we actually produce a smaller model even for a big rocket, we produce first a smaller model and then we test it. Usually for test the aerodynamic of planes, what they do is they just first build a small structure and then they check in wind tunnels that how the aerodynamics of the car or the aerodynamics of the plane works actually in actual scenarios. So this modeling purpose, you need to shrink the huge structure. For that shrinking huge structure, we can use this dimensional analysis, because we can convert units by using this dimensional analysis. So, but in A-level syllabus, we do not go much deep into that one. So, this subject, this dimensional analysis subject, is not just finding the dimension of a physical quantity. It has far more uses, right? In A-level syllabus, we have to discuss two types of applications of dimensional analysis. So we will discuss only those two, because applications beyond that will not be in your examination. And if someone is interested, actually you can study on that one, you can search on that one, you can Google it actually very easily, you can learn about that. But for the A-level examination, we have to know about exactly two applications and we have to be fluent in those two applications, right? Okay, so the first application that we can take is this dimensional analysis of the dimensions we can actually use to find the units of a physical quantity. We can use this dimensions of a physical quantity to obtain units of a physical quantity. For an example, if I take force, right, or if I take if I take force, the dimension of force was m l t minus 2, right? This was the dimension of force. You can go back and check. So if you need to find the unit of this one, I am referring here to basic unit. So the basic unit of force you can easily get by using dimensional analysis. So the basic unit of force, capital F, you can write down as, so we know capital M definitely is a mass, right? Capital M means the symbolic, in the symbolic format, capital M is a mass. So the unit of measuring mass is kilograms. And this is capital L, definitely it should be a length. Therefore you have to put unit as simple M. Then this is capital T, means it is a time, therefore it should be measured in seconds. S, and we have minus 2. So the basic unit of force is kg ms minus 2, right? So this is actually called as Newton also, but you can easily calculate, you can easily find the basic unit of force by using the dimensional analysis. So for a small application like this seems very, very simple, right? You don't need dimensional analysis to find the unit of this force, because you already know the unit of force is Newton or this one. But if you see a physical quantity that you don't know, for an example, I will tell you gravitational constant, universal gravitational constant. There's a physical quantity called that, universal gravitational constant. So now you don't know any relationship between the fundamental physical quantities and the gravitational constant. So by using dimensional analysis, you can build up the relationship. Then you can actually find the basic units of that one. So that is the main use of dimensional analysis. Okay, so we will do few examples on that one first, right? You can write down like this. Write down several under advanced level or under A-level scope, we have few applications of dimensional analysis. We have few applications of dimensional analysis. I will break there are basically two things, but I will break and tell you. Then we can have a few more applications also, right? So the first one, you can write down, to obtain basic units of a physical quantity. To obtain basic units of a physical quantity. To obtain basic units of a physical quantity. Second one, to check the correctness of a given relationship between physical quantities. To check the correctness of given relationship between physical quantities. I will explain that one. Third one, to derive expressions among physical quantities. To derive expressions among physical quantities. Right. So these are the basic applications of dimensional analysis. So you will get question either from one. Okay, you will get either from the first application or the second application or the third application. Sometimes this can get as a part of another question, right? For an example, we have a lesson called let's say properties of materials. So in this properties of material question, there are a lot of equations. In physics syllabus we have a lot of equations. So in this lesson, sometimes you will your first question may be show that this equation is correct by using dimensional analysis. That may be your first question, because if you go through the past papers, you can see it like that, because their first question is not from directly a question or a simplification. Their first question is actually check whether the equation is correct or not. If this is correct, then you can use it to the other questions, right? So that is the importance of learning this part well. Okay, so now we will go one by one. Okay, so we will write down the subtopic, obtaining basic units of a physical quantity. Obtaining basic units of a physical quantity. Right. We will not do the simple one. We will do some special questions on that. Right? Okay. First one, we have to obtain the physical quantity of. I will tell you what is the physical quantity that we have to find the basic units. Okay. So the first equation that I will give you is F equals G capital M simple M divided by R square. Right? So this F represents a force, G is called the universal gravitational constant, capital M is a mass, simple M is another mass, and simple R is the distance between them. So if I draw a very small sketch, then you can understand this one. So let's say this is capital M, let's say this is simple M. These two are objects, actually masses, and simple R represents the distance between them, and capital F represents the force between them. This is the equation that we will find in future lessons, right? This is the expression and the components of that equation. Now we have to find the basic units of capital G, right? Okay. So how do we start is, first we find the dimensions of capital G, then through that one we are going to find the basic units of capital G. Sometimes your question may be directly to find the dimensions of capital G, sometimes it may be the basic units. So either one can come. Therefore we should be ready with we should be ready for anything. Okay, right. Now start to try this out. Okay, now we'll see how to do this one. So first we write down the equation again. G, capital M, simple M, R square. Please follow these steps. Okay, that is important. Then you can apply the dimension mark to say that you are finding the dimensions. G. Please apply the dimension mark to all the terms separately, right? Like this way you can apply to each term separately. Right? For here you can put the square outside, no issue. You can put the square outside as we mentioned earlier, R and square of that. Now you can substitute. Now you know the dimensions of force, that will be M, L, T minus 2. So when you do some examples, then you will automatically remember this one, right? Because this is not changing. Dimension of force is a fixed thing, it will not change. This is capital G, mass is capital M, again another mass that is also capital M, divided by L to the power 2. Now if you simplify this one, you have M here and another M here, you can cancel out that one. Now you can cross multiply this capital L square to the left side. So when you are multiplying, it will come to the numerator. So L square multiplied by L, you will get L to the power 3 equal, L to the power 3 times T minus 2 is remaining there. T minus 2 is remaining there, and you have remaining capital G and capital M in the right hand side. Now you can take this one over to this side, then it will become M minus 1. Therefore your final answer is M minus 1, T minus 2, L to the power 3 equals capital G dimension. Usually we do not keep an answer like this. Usually the answer, when you are writing the answer properly, then please take this capital G to the left side and keep all the other terms in the other side. So if I write this one properly or rearranging, capital G is equal to M to the power minus 1, L to the power 3, T minus 2. You can interchange these terms, no issue. You can put capital M to the end, take the L to the power 3 to the front, no issue. You can interchange these terms. Okay, I am just writing this one in the other way around. You don't have to put minus sign, no anything. You don't need. You just turn the equation and write that. Now you can put the units of each term. So the basic unit of gravitational constant you can easily take. M to the power 1 means kg minus 1. Here L means meters, length M to the power 3, and seconds S minus 2. So this is the basic unit of universal gravitational constant. It is not that difficult, it is very easy. You can easily calculate that one. Please take this down, clear, yeah? Don't skip, don't try to just to copy down, right? Try to do it yourself. Okay. Right. Don't worry if you miss to write down. You just write down the first part and you just write down the answer. Then the simplification you try to do alone. Okay. Now we will do another one, right? Okay. Next example, we have an equation in physics, that is force is equal to neta capital A V over D, right? I am not sure that I have written this equation last week also, but however this is the given equation. Here F is the force. You can write down in the front what are the terms here. Capital F means that is force. This capital A means area. V means velocity, and D means distance. This one is called neta. Neta, capital N, an extended part like a tail for N. We call it neta. It's a Greek symbol. We call this viscosity. Right? Okay. Now you have to find the dimensions of viscosity. You have to find the dimensions of viscosity. Right? Quickly try to do this one. Don't bypass or don't try to skip the process. You have to put the dimension mark, then you have to simplify quickly. Right? Okay. You can refer to the previous one, okay? Where you have taken the dimensions of force, where you have taken the dimensions of area, where you have taken the dimensions of velocity. You can quickly refer them, refer that page, and you can find the answer. The important thing is you have to try, yeah? Please try at once. Okay, I will also start with you. Right. First thing is you have to put the dimension mark. Take F equal neta, dimension, area, dimension, velocity, dimension divided by distance, dimension. Now we have to substitute the dimensions correctly. Dimensions of force was M, L, T minus 2 equal dimensions of neta. You have to keep it with the square unit of square bracket. Keep it with the square bracket. Then area, that is L squared, velocity L T minus 1 divided by L. Not that difficult, no? Very easily you can find the dimension. Here capital L will get cancels out. Then you have to take this one to this side. Therefore, what happens? Another L get cancels out, right? Here there is one L. Here L squared. One will get cancels out. Therefore, what is remaining is M. T minus 2 is remaining there. You need to take this one to this side. Therefore, when you are taking this one to this side, your power become minus, right? Because you are taking this one to the denominator. From denominator, you again transfer it to numerator. Then it will become L minus 1. And when you are taking this one to this side, T minus 1, when you are taking it to here, it becomes T plus 1 times equal to neta. Now you can write down easily. Dimensions of neta is equal to M here, and L minus 1 is here, and T minus 2 and T1, T plus 1, minus 2 plus 1 means minus 1, then T minus 1. So this is the dimension of viscosity. This is the dimension of viscosity, right? In your A-level examination, you will be directly asked you are not given this equation, because you are learning this one in future lessons. So they are directly asking what is the unit of viscosity or what is the dimension of viscosity. That is the only thing that they ask. Okay, so you have to know the equation also, but here as you do not know the equation, I am giving you it, right? Okay, right, now we did some examples, 2 examples. Now we will move to the next application of this one, right? Second application, write down, checking the correctness of a equation or expression. Checking the correctness of a equation. Checking the correctness of a equation. Right. So now when we are going to check the correctness of an equation, there are a few rules that we need to know. Now without knowing these rules, you cannot actually do this application. So you need to know these rules. So we will go one by one. You can write down like this way: rules of dimensional analysis. Rules of dimensional analysis. Rules of dimensional analysis. Rules. You don't need to keep them all in the same word. Sorry, you don't need to keep every statement like as it is. You don't need like that. You just take the idea. That's enough. Taking the idea is more than enough, right? So the first rule is. So let's imagine you have physical quantities separated by a plus mark, a minus mark, and an equal mark. So this is an expression showing relationship between actually 5 physical quantities. So A is a physical quantity, B is a separate physical quantity, C another physical quantity, D another physical quantity, and E is a separately another physical quantity. So each of these physical quantities are separated by plus mark or minus mark or equal mark. All these physical quantities are separated by mathematical symbols like plus, minus and equal. Only these 3, right? Only these 3. These are separated by plus mark, minus mark, equal mark, right? Now just say something like this. So the rule says if you are adding, if the physical quantities are separated by a plus mark or a negative mark or an equal mark, then dimensions of each term, not physical quantity, each term means this one, this one, this one and this one. These are terms. Dimension of each term must be equal. That means A and B are separated by a plus mark. Therefore, dimension of A must be equal to dimension of B. And B and CD whole term is separated by a negative mark. Therefore, the rule says if it is separated by a negative mark also, these 2 terms must have the same dimension. The term means here the whole C and D at once, taken together, C and D taken together. And third one is, so C, D and E are separated by an equal mark. Therefore, the dimension of C, D must be equal to dimension of E. So if you take this equation, all the terms in this equation must be dimensionally equal, right? Right, this is the first rule. You can simply write down like this. First, we will write down this statement, then we will write down the expression. Okay, write down. if physical quantities are separated by, if physical quantities are separated by plus mark, minus mark or equal mark, then dimensions of each term, then dimensions of each term must be equal. Then dimensions of each term must be equal. Dimensions of each term must be equal. Right, that is the first rule. That means if you separately find the dimension of A and if you separate the dimension of E, there is dimension of A and dimension of E must be equal. Let's say due to something or the given equation, for the given equation you don't get that dimension of A is equal to dimension of E. So you get dimension of A not equal to dimension of E. That means your equation is completely incorrect, right? So if they are separated by these 3 marks, that must be equal. If you are getting that they are not equal when you find the dimensions separately, then that says that your equation is completely wrong. Okay, so through that one you can check the correctness of the equation, right? So this is something like this. No, can you add area to a length? So area is another physical quantity, length is another physical quantity. Can you add 2 meters to 5 square meters? Can you add these two? This is like adding apples and coconuts, right? Can you add apples and coconuts? I have 5 apples and 2 coconuts. What is the answer? Is it possible to give you the answer for this one? No, this is not possible. No, how to add apples to coconuts? It is neither 7 apples, it is neither 7 coconuts, right? So you cannot add 2 different physical quantities, right? If you need to add 2, you can only add 2 masses. You can add 5 kilograms to 5 grams. That is okay. Unit is different. 5 kilograms to 5 grams. Both of them are masses, right? If you take the dimension of this one is capital N and dimension of this one is also capital N. So when you have 2 equal dimensions, then you can add, because same physical quantity, same type of physical quantity. Not like this, right? So 2 meters plus 5 square meters, it doesn't make any sense, right? So be very careful when you are adding the or subtracting or equaling the physical quantities. So if you get the dimension of this first term is not equal to the second term, which is separated like this, then definitely the equation given is not correct, right? That is how we are going to check, right? For the multiplication and division, this doesn't hold, okay? For that it can change, but for these 3 symbols it is fixed. It must be equal. So this is the first rule. The second rule is if you have a power of a physical quantity, let's say physical quantity A is equal to physical quantity B times C of C to the power T, something like this. So you have the physical quantity A and that is equal to B to the power C T. So the rule says that dimension of CT equals 1. Dimension of CT equals 1, right? Because these two are separated by a equal mark. Therefore, dimension of A must be equal to dimension of B to the power Ct. To satisfy that relationship, definitely the dimension of Ct must be equal to 1, right? Therefore, if you have this kind of relationship in an equation, then the theory says that dimension of the power is equal to 1. Dimension of the power is equal to 1, right? Okay, that is the thing. So if t is time, then you can separate and do the simplification, that is correct. But if you take the whole power, then the dimension of whole power is equal to 1. That is the idea here, right? Okay. Now write down the second one. Write down power of a physical quantity. Power of a physical quantity. Power of a physical quantity has no dimensions. Has no dimensions. That is why we are putting as 1, right? Has no dimensions. Power of a physical quantity has no dimensions. Therefore, dimension is written as, plus 1. Therefore, dimension is written as 1. And write down this one. So for the first one also, I think you have already written this one below the sentence. Okay. If you haven't written this one below the sentence, please note that down also. After writing the second statement, as an example, you can write this down. And I will write another example here. Now let's say you have x equals y to the power ab plus c. Then here the theory says that ab plus c dimension equal 1. The whole, because this ab plus c is the total power here. So the total power has no dimensions. Total power has no dimensions. Right, okay. Third rule, right? Now in equations, or in many of the equations, you can have numbers, right? You will get numerical values like 1, 2, 3, 4, half, like that way you can have numerical numbers, as well as you can have numerical constants. For an example, you can have numbers like 2, 3, half, as well as you can have special numbers like 5. So 5 is a special number. So it is not a physical quantity, it is a number. So 5 represents 22 divided by 7. So this is a numerical constant. 2 is a numerical constant. So if you find numerical constants in your equation, so these numerical constants does not have dimensions, because number 2 is not either a length or a mass or a time. It is just a number. So numbers do not have any units as well as dimensions, right? So if you find any numerical value, numerical constant in your equation, you can just put 1, because as I mentioned earlier, so the symbol, so if you don't have any dimension to the physical term, then you put 1. right? Not 0. Don't put 0. Then what will happen is everything will become 0, because anything multiplied by 0 will be 0 now. So in an equation, if you put something 0, anything multiplied by that one will be also 0. To avoid that one, scientists have introduced put 1. If you don't have dimensions, do not put 0, just put 1, right? So if you get any numerical constant, so the dimensions of numerical constant is always 1, like that thing, 1. If you have dimensions of half, that is also 1. Dimensions of 5, that is also 1. Right? Don't put 0, but just put 1. Okay. Third point, write down. Dimension of numerical constants. Dimensions of numerical constants. Dimensions of numerical constants is taken as 1. Is taken as 1. Is taken as 1. Right? Dimension of numerical constants is taken as 1. Right? Write down these examples like this way. You can write down the examples. Right, okay. So these are the basic rules that we have to use for the dimensional analysis. Okay. There's one more rule. Okay. Write that down also. That physical quantities without dimensions. Fourth one, the fourth rule is physical quantities without dimensions. Because there are some specific physical quantities that you do not find any dimension. So we have a small list of physical quantities because they are some bit special. Therefore, if you find these physical quantities in any of the equations, then you can say that they do not have dimension. So we will take that list down. So the fourth rule will be physical quantities without dimensions. Physical quantities without dimensions. Right, for an example, first thing is if you have any angle, then angles do not have dimensions. So as I mentioned earlier, if you do not have a dimension, what you put is 1, right? Okay. Then there's a special physical quantity called relative density. We will learn them later. What do you mean by relative density? So relative density do not have a dimension. Therefore, we put 1. Next one, we can take coefficient of friction. Coefficient of friction. Dimension of coefficient of friction is also 1. We have another special physical quantity called relative humidity. We will find them in our upcoming lesson, so don't worry, I will explain them when we meet there, right? So for now, just take these important physical quantities right now. relative humidity, that also do not have dimensions. So these are few special things. So when we are learning the subjects and when we are getting the more and more equations, then each and every time that we write in an equation, we will write down the dimensions also. Okay, so don't worry if you didn't get them. We will get these again and again in our lessons. For each time I am writing an equation, I will ask you to write down the dimensions. So then you can practice throughout the syllabus, right? So these are the 4 basic rules that I have to highlight when you are going to find the dimensions of any physical quantity, or when you are going to check the correctness of any relationship between physical quantities, right? Okay, now we will go to some examples. Okay, we will go to some examples. Write down examples. I will do the first example and then you try to do before me, okay? You try to do it before me. I will use a very simple one, right? Let's say we have an equation like this. This is a simple equation. S equals ut plus half at square. So this is an equation in linear motion. So what is asked is to show that this equation is dimensionally correct. Okay, or you have to say whether this one is dimensionally correct or not, right? I am not saying this is correct or not. So you have to say whether this is dimensionally right or wrong, right? So I will define the terms in the front, then you will try to start. Okay, so the first thing is S means displacement. S is a displacement. These are some standard symbols. Okay, S is displacement, U equal velocity, T means time, A means acceleration. Okay, now please listen carefully. I am going to show how to do this one. So what do we do is, when you need to show this one is dimensionally correct or wrong, what we do is we take each term separately. So you have 3 terms. The first term is displacement. So we will analyze the dimension of displacement separately. Then you have product ut. You have a term called ut. So we will analyze this ut term separately. And we have another term half at squared. So we will analyze this part separately. So that is how we do this one. Because if this one is dimensionally correct, these are separated by equal mark as well as a plus mark. Therefore, if this is dimensionally correct, dimension of S must be equal to dimension of ut and dimension of half at squared, total term. That is the thing. If this is dimensionally correct, dimension of S must be equal to dimension of ut equal dimension of half at squared. That is the requirement for this equation to be correct. Now we are going to check whether it is true or false, right? Okay, we will take displacement separately. So S, dimension of S. So S is a displacement, therefore dimension is L. That is all. There's nothing to worry about that one. S is displacement, therefore unit dimension of displacement is capital L. That's all. Now we come to ut. So the dimension of ut. So I will use this space, right? I will write it from here. Okay. I will take ut. Now I have to find the dimension of ut. So you can first separately write down u and t. So you know u means the velocity. So the dimension will be L t minus 1. And dimension of time is capital T. Now t to the power minus 1, capital T, that is t to the power plus 1, minus 1 plus 1 becomes 0. So L t to the power 0. So t to the power 0 means 1. What? power of anything, if the power of anything is 0, that means answer is 1. In all levels we have learned, no? X to the power 0 equals 1. 10 to the power 0 equals 1. So power, if power is 0, answer is 1. Therefore t to the power 0 means 1. Therefore your dimension is capital L. Dimension of S is also capital L. Dimension of UT also capital L. Now you are halfway through. Now we have to check this term also. We will take it separately. Half AT squared. Now write down the dimensions. So you can see here half, we have a numerical number, half acceleration t to the power 2. Substitute the values. So you have a numerical constant like half. So the dimension is 1 times Lt minus 2. That is acceleration, no? You can refer to previously defined ones. And you have t squared. So t to the power minus 2 here, t to the power plus 2 here, same like this one. So it becomes 1. So get cancels out. So the final is capital N. Now see here, though they seems totally different. Okay? So S is we do not see any similarities between these three terms. They are completely strange. Right? This is only one letter. There are only two letters are there. Now there's a whole big expression there. So by just looking at this one, we can't say anything. We can't actually relate these three terms if we have given separately. But see what the dimensions can do. So the power of the dimension is, you can see the dimension of SL is also L. Dimension of UT term also L. Dimension of this whole term is also capital L. That means though we have completely dissimilar terms, when you simplify and take the final dimensions, they are equal. Therefore, you can clearly say, can clearly write down, I will erase this one, dimension of S is equal to dimension of UT equal to half AT squared dimension. So this is a must, okay? You have to write this down. Because of this, therefore, you can write down equation is dimensionally correct. Equation is dimensionally correct. So you have to write this down. If it is an MCQ, you have nothing to write down. But if you have get this one in your essay question paper, then it is a must to write down this one, right? So finally you have the answers. You have to show these things. You have to get marks for each of them. Then writing this one, you have marks, and for writing this one, you have marks. Because finally you have to say the conclusion. This is the conclusion. In physics, you have to give the conclusion. What is your final conclusion on the answer? Right? You have taken relationships, so what is the conclusion that you can have? Okay, this is the first example. I hope this is very, very clear to you. I did it very slowly, so I think it is clear. Then we can go for more examples. So first, take your time, write this down clearly, okay? Don't jumble, just clearly write this down. Right, okay. Now we will do another example. Quickly we will do. And because we have to discuss the other application also. So I am not rushing through. If I am too fast, please let me know, okay? Because we have enough time. Because we are having 2 weeks per day, 2 days per week. So no need to rush. So, but if you have any question, any doubts, anything not clear, please just raise it, okay? Okay. So the next one I am giving you, the next expression that I would like to do is I will say this one. P plus half rho v square plus h rho g equals to some constant value with the physical quantity. So this k have k is a physical quantity and it can have dimensions. Okay, I don't worry about this k much, but I worry about these three terms, right? So you have to say this expression is dimensionally correct. So you just don't think about k, right? You just no need to think of k. You have to just think of these three, right? So if you can say, or if you can show that the dimension of this p is equal to dimension of this one and equal to dimension of this one, that is enough. You just don't need to show that, you don't need to think about this k value. That's a constant value. Okay, that means a constant with the dimension. That is something like gravitational constant, like that way. Not a numerical constant. Okay, I am especially saying this is not a numerical constant. Some constant like gravitational constant, gas constant, like that way. Right? So the terms here I will define as, here P means pressure. P means pressure. So rho means density. V means velocity. Write with me. And H means height. G means gravitational acceleration. Gravitational acceleration. It is, however, an acceleration, right? It's an acceleration, right? Now quickly try to prove this equation is dimensionally correct or not. This is our second example. So what you can do is, you can separately take each term and write down the dimensions, right? So you can also try, while you are also writing down, I will also write the answer here. So if you take that, we have previously find the dimensions of pressure, so I can directly take that one here, right? Then I have half rho v squared, total dimension equal half dimension, density dimension and velocity dimension squared. Now you can substitute here. This is a numerical constant, therefore the dimension is 1. You have density here, if you can remember, m L minus 3. And if you have, now we have velocity here, that is L t minus 1 to the power 2 is there. Now you can simplify this one. M L minus 3 L to the power 2 t minus 2. So for now, write down each step, okay? Because I know some of you can just simplify, okay, without even expanding. You may be able to simplify this one, but don't take a risk, okay? For now, write down the expansion correctly and try to avoid your mistakes. Once you are getting more experienced with these kind of simplifications, then you can miss some steps, okay? So basically, usually maths students usually can skip some steps, right? And usually biology students, they are not able to quickly, some of the students, they are not able to quickly go through the simplifications. That is the normal behavior that I have seen. But the thing is, mostly biology students get the answers correctly and maths students get incorrectly. Now what is the reason is, maths students have high confidence that they can simplify fast and they are skipping some steps. Then ultimately what is happening is, they are missing something. But those students who are writing every step and clearly, they will never miss the answer. Right? So don't get overconfidence till now. Don't get overconfidence now. You can get overconfidence when you have done a lot of examples, right? Until that one, please clearly write down the steps. That is necessary. Okay. Now you have L to the power minus 3, L to the power 2 here. That will give you ml minus 1. And you have t minus 2 here. So you can see here, we are getting a similar result as here. Okay, now it is good because now we are in the correct path. Now you can separately find the dimension of H rho g. I hope you have written down this one. Now we will find the dimension of H rho g here separately. So H is a height, rho is a density, and g is gravitational acceleration. Okay, quickly you can substitute here L. Here rho means m, L minus 3. Here g means acceleration, that is Lt minus 2. So you have take m to the power, m to the front. You have L squared, and minus 3 is there. ml minus 1, t minus 2. Right, such a beauty. You see, ml minus 1, t minus 2, ml minus 1, t minus 2, ml minus 1, t minus 2. All these three terms has the same dimension. So you can proudly say, dimension of pressure P equal dimension of half rho v square equal dimension of H rho g. Therefore, this expression or this equation is dimensionally correct. Therefore, equation is dimensionally correct. Right. I hope this is very clear. If you have any doubts, please raise. Right. I hope time is enough for you. So we have the, one question about the previous one, that is about the constant k. Yes, though I have written it as a simple k, a constant value, it is actually also a pressure, right? Because you will learn this equation in fluid dynamics as the Bernoulli's equation. So the equation that I have written previously is the Bernoulli's equation, and in the Bernoulli's equation, what we do is actually we write down the same expression for two places. Okay, sometimes you may not understand right now, but in Bernoulli's equation what we do is we write down the same equation for two physical points. Okay, two places in a fluid. So when you are writing the expression to two places, the thing is that the Bernoulli's theorem says that all the values, all the summation of values that I have written there must be equal in both places. Okay, something like that. That means if you have two places like 1 and 2, if you take P of first place, half rho v squared of the first place, and H rho g of the first place, that complete summation is equal to the same values at point 2. That is what Bernoulli says, right? It is something like that. So the first term is 1, second term is 2, third term is 3, assume like that. So in the second point also you have 3, 1 plus 2. Still each term has different value, but final summation is same, no? you have P a separate one, H half rho V squared value 2, like that way you have 3 different values in first place and 3 different values in second place, but when you take the sum they are equal. To show that one we are putting that K value, that K is also a pressure, K is also a pressure, right? So in the Bernoulli's expression, when you are writing it down, the thing is we are actually writing to 2 places, writing for 2 places, that is the case, right? So now we will do this equation, we will analyze this expression quickly. I don't need, I can remember the values, so I will not write down. So we will go one by one. So you have to take the V over T term first. You take the V over T term first and you write down the dimensions. So volume dimension divided by time dimension, L to the power 3 divided by T. Therefore the dimension is L to the power 3 T minus 1. This is the dimension of left hand side. This is the dimension of left hand side. Then we have to take the dimension of right hand side. So that will be 5 P R to the power 4, sorry, R to the power 3, no, not 4, sorry, R to the power 3 divided by 8 neta L, all the dimension. Now you can break into small pieces. 5 P to P R to the power 3 divided by 8 dimension neta dimension times L dimension, right? Now you can substitute in each term, you can substitute the values for each term. Phi is a constant, therefore numerical constant 1. Pressure, if you can remember, M, L minus 1, T minus 2. And here that is radius, that is L to the power 3. Divided by 8 is a numerical constant, therefore dimension is 1. Neta, what was the dimension of neta? Dimension of neta was M L minus 1 T minus 1. M L minus 1 T minus 1 times capital L. Please tell if I am wrong, okay? Here the dimension of neta was M L minus 1 T minus 1. Right, now you can easily simplify this one. You can see here mass is getting cancels out directly, right? Top here mass here cancelling out. You can see here again L minus 1 here cancelling out, right? Sorry, not here, no, not here, it should be not L minus 1, no? Yes, it is L minus 1, that is correct. Here you have T minus 2 and below that one you have T minus 1. Therefore, you get it T minus 1 and here you have L squared. So finally what you get is L squared T minus 1. This is the dimension of right hand side. So we have separately find the dimension of the left hand side, that is V over 2, V over T, that was L to the power 3 T minus 1. The second one was the right hand side dimension was L squared T minus 1. So you can clearly see that they are not equal, right? Therefore you can write down the conclusion as, right? I will write down here left hand side dimension. You can write like that way, right? Rather than writing down this whole expression, you can write down left hand side dimension is not equal to right hand side dimension. So these two dimensions are not equal to each other. You can clearly see. Therefore, you can say equation is dimensionally not correct. Therefore, equation is dimensionally not correct. So sometimes they can give these kinds of incorrect equations and you have to check whether that is correct or wrong, because always you may not get the correct equations. They will give or they will mislead you by giving a wrong equation. So you must be very careful when you are writing the answers. Right. Please take this now. Please take this down. So you can write down the third application of dimensional analysis: building up relationships or constructing relationships between physical quantities. Constructing relationships between physical quantities. Constructing relationships between physical quantities. That is our third application. I will use this space also to write questions. Right. This is the most important one, okay? So, because this is a beautiful application that you will see in dimensional analysis. This is very, very interesting, right? Because you can use this, actually every day you can use this one. And you can check whether the equations that you have, or you actually, rather than checking the given equations correct, actually you can derive the equations by using this one, right? That is the beauty of this one. So if you know that some physical property is depending on these physical properties, some other physical properties, then you can derive a real application, real equation which is showing the exact relationship between physical quantities. So if I say like this way, so if you consider, let's say, so this is actually the most classical example that you get in our syllabus, but it is very interesting to do. So let's say you have a simple pendulum. So what do you mean by a simple pendulum is, this is a string connected to a small mass or a small marble. So a marble is here, that means a mass here, and we are connecting that mass to a string, very small, very thin string, and we are fixing it to somewhere in the top. Now what you do is, now you let it move side to side like this way. You let it slide, let it move like this way. You just drag it here and you release. Then what will do it will go to a periodic motion or repetitive motion. It will go to a repetitive motion. You can see this one every day, right? If you just keep your pen like this, and if you give a small push, or if you pull this one and release, then what we will see here, if this end is free, then you can see some kind of repetitive motion here, right? Through a string, this is very much possible if you use a string and a mass, right? So this is not a very huge application of physics, but this has a very interesting application. Okay, so the theory says that the time taken by this pendulum bob or the pendulum to complete one cycle, that time period is depending on 3 factors, right? So the thing is, now the time taken, again I will repeat this one. So now you will see that you have connected this one to by using you have connected this mass to a fixed point using a string. So I will put some labels here, then it is easy. Okay, so let's say mass of this pendulum is simple m and length of this connection is simple l. Okay, and we have the gravitational acceleration acting downwards because it is always present everywhere. So we can put capital simple G for the gravitational acceleration. So let's say, it has been experimentally found that the time taken by this mass to complete one complete cycle, that means if you start from here, it will first go here and then come back here. We call it a one cycle. So it is said that this time taken to complete one cycle depends on length of the pendulum, mass of the pendulum, and gravitational acceleration. It doesn't say any kind of other relationship. It only says that if we take periodic time or the time taken to complete one cycle as t, then it is said that this t depends on m, l, and g. This is the only thing that we know, right? We know that this will depend on m, l, g. So if you are not knowing that one, in a question they will give that. So this t will depend on mass, length, and gravitational acceleration. So what you have to do is you have to find the exact relationship between m, l, g, and t, right? The only thing that you know is the dimensional analysis. So how to use dimensional analysis to do something like this? So it is very interesting. Now see here. So it is said that this capital T depends on M, L, and G. You don't know anything, right? So what you do is first you write down a hypothetical expression. Right? Hypothetical means you think and write. So we will say, I will assume the relationship is something like that. We will say the periodic time or the time taken, capital T, is directly proportional to m to the power x. We do not know the value of x, but we will write down this t is proportional to m to the power x, l to the power y, and g to the power z. Right? Because I know that t depends on m, l, and g, therefore I just write down t is proportional to m to the power x, l to the power y, g to the power z, where x, y, and z are unknown to us. We do not know the values of x and y. Right? Now in mathematics, if you have something like this, if you have a proportional relationship, you cannot do any mathematical operation. Okay? To do any mathematical operation, you have to convert this one to an equation. So equation means you should have an equal mark in between left side and right side. So in mathematics there is a technique to put an equal mark here. So the technique is you can put an equal mark as well as a constant simple k in front of the equation, and you can write down like this. Right? So this is a mathematical trick. This is a mathematical trick to convert proportional sign to equal sign. So we call this k value as proportionality constant. Right? This k value is called proportionality constant because I use this k to eliminate this proportional mark. That is why we call this proportionality constant. Right? The important thing here is I am the one who is putting this k here. Right? No one is giving there something value called k. No one is giving. I am the one who is putting this k value. Therefore, it is essential to write down that this k does not have dimensions. Right? We know that k does not have dimensions. T will only depends on m, l, and g, because the dimension always says that how physical quantities are related to another quantity. So I need to say that this K is a quantity, it's only a value, not a physical quantity. Therefore, this T value does not depend on K. Therefore, I have to write down, once I put this equal mark and K, I have to write down within the brackets, K is a dimensionless constant. So you have to write down this one as soon as you put the equal mark and constant. K is a dimensionless constant. That is to say that K does not affect the equation. That is to say that K does not affect the equation. Okay. Now, what can we do? So, you have now equation. Now you have an equation. Therefore, we know that from the first rule, if something is separated by an equal mark, the dimension of this one must be equal to dimension of this whole term. So now what we do is, we do that equating. We are going to equate dimension of T to dimension of right hand side terms. So now what I do is, I can write down left hand side dimension. Left hand side dimension is, we want in left hand side I have only capital T. Therefore, capital T is the time I have taken. So the dimension of capital T is capital T. So this is the symbol of periodic time. This is the symbol of, is a dimension of capital T. Don't mix up like that, okay? So it is better if I can use a different symbol for this one. So I will say but the standard symbol for this repetitive cycle is capital T. That is why I have written the capital T here also. So this capital T represents periodic time. This capital T represents dimension of periodic time. Like that way. Okay, because we have some standard symbols in physics, and when we are writing the equations, it is easy if we use the standard notations. So the standard notation of this periodic time is capital T. Right? Okay. Now you can write down the dimensions of right hand side, and you can equal both sides. Right? So what we have is K m to the power x, l to the power y, g to the power z dimensions. Now you can separate each term. K dimension, m dimension to the power x, l dimension to the power y, g dimension to the power z. Now you can write down K is a dimensionless constant, therefore you can put 1 here. Here you have m, then m to the power x. Here you have length L to the power y, and you have acceleration here L t minus 2 to the power z. M L t minus 2. Here it is minus 2 power z. Right. So the next step, you can take equal bases and you can add the indices. So what you have is, you can do one more expansion here, that is m to the power x, l to the power y, l to the power z times t to the power minus 2z. T to the power minus 2z. So you can write like this. Okay. So I will use this space. Okay. So we will first write down the question, and then we will go step by step. Okay. Because I need to erase this part. So let's write down like this. So the third application is, we have, I think, written down the application. Now we can write down like this. write down the periodic time, the periodic time, the periodic time of a simple pendulum, the periodic time of a simple pendulum within brackets capital T, within brackets capital T, depends on mass of the pendulum, within brackets simple m, within brackets simple m, length of the pendulum, within brackets simple L, and gravitational acceleration, within brackets simple G, full stop. Derive an expression for periodic time, by using dimensional analysis, Okay, first draw this diagram and first you write down up to this limit, right? After coming here, you can write down this up to this point, okay? Okay, now we will go to further simplification, right? So I will have to erase this part. Now we will do the simplification. I will remove the diagram also because we have already drawn this one. Right. Now if you go to the simplification here, the right hand side simplification, RHS side, you have now capital M to the power x. Here you have two L terms. Therefore you can write this one as L to the power y plus z. And you have t to the power minus 2z. So now we know that it is given as an equation now. Therefore what should happen is the right side dimension must be equal to left hand side dimension, right? Therefore you can write down, therefore left hand side dimension is capital T and it must be equal to right hand side dimension m to the power x, L to the power y plus z and t to the power minus 2z. Right. Now you can see here, now if you compare these two expressions, two sides, here in this side you only find capital T, right? You don't find any capital M term. You don't find any capital L term. You only find capital T term. So what you can do is, now you can equate powers in both sides, right? Now if you consider mass, power of mass, okay, I can write down something like this first. Comparing powers, power value, okay. So here you don't have any power of m, you don't find any m term here. Therefore what should happen is, if you consider the powers of m, left hand side powers are equal to 0. No power means 0. No m term means power is 0. And here you have x. Therefore you can get x is equal to 0. Therefore, x is equal to 0. Then similarly you can equate the power of t, because you have t both sides now. So you can equate the powers of capital T. So in the left hand side, the power of t is t to the power 1. This is only t, no? T means, we have only t means power is 1. T to the power 1. And in the right hand side you have minus 2z. So from here you can take that z is equal to minus 1 over 2. Z is equal to minus 1 over 2. Right? Now you can take the L term. So if you take the L term now, you have no L term in left hand side. Therefore the power must be 0. But in right hand side you have L to the power y plus z. So this one will give you that y is equal to minus z. Right? Y is equal to minus z. So you know that z is minus half. Therefore minus minus means become plus. Therefore y is equal to plus half. So these are the answers of x, y and z. X is coming as 0, y is coming as plus half, and z is coming as minus half. Right. Now we have the powers of each term. Now what we do is, now we will plug these values back into our original equation, our original expression. So what is our original expression? That was t is equal to k times m to the power x means 0, L to the power y means half, g to the power minus half. So I have plugged in these values x, y, z into our original expression. So m to the power 0 means 1. So k times 1. Here you have L to the power half and you have g to the power minus half. So you can remove this minus sign by taking this one into the denominator. So you can write down this one as g half. Right? When you take this term into the denominator, you can remove the minus mark. When you are taking this one to the numerator, you can again put the minus mark. So here also now you can write down t is equal to k times, you see here both L and G have half power. So you can put a single bracket like this and you can put a single power, because you have the half power in the numerator, also half power in denominator. So as the power is common for both denominator as well as numerator, you can put a single bracket to the whole term and you can write down the power outside. So the half power means what? Actually the half power means square root. Therefore finally you can write down that t is equal to k times L over G square root. So you see here we have get a very beautiful equation between t, L, G and M. So this equation says that M is not here. So what does that mean is, though we assume that this periodic time capital T depends on mass, actually it is not depending on mass. If it was depending on mass, you will have a term called simple m in the equation. But in the final equation, we do not have any term called mass. That means this periodic time does not depend on mass. Right? So, but we assume that it is depending on, but our assumption is wrong now. So, this is a very powerful tool. The dimensional analysis is a very powerful tool when it comes to deriving equations. So where we started was we didn't know anything much. We only knew that the periodic time capital T only depends on mass, length and gravitational acceleration. That is also was an assumption only. So we started with an assumption. So with that assumption we do the dimensional analysis, and the dimensional analysis will give us the exact result. So this is our exact equation. So there's only one doubt here, only flaw here. The only flaw is you cannot calculate the value of constant k. So you have to do an experiment or any other method to find the value of k. So the dimensional analysis also have limitations. So you can see a limitation here. So though you can obtain a clear relationship between physical quantities, it is not possible to use dimensional analysis to find the numerical values of constants. Right? We can derive expressions, we can obtain relationships between physical quantities, but it is not possible to find the numerical value of constants. So you just have to keep that in mind, right? Okay. So if you haven't completed this one, so quickly write this down and complete this one. Now we will try another example, right? We will try another example. So these are basically very classical examples, right? So you can write down like this. The force acting on a particle, the force acting on a particle within brackets capital F, the force acting on a particle within bracket capital F, moving in a circular path, depends on mass of the object within bracket simple m, speed of the object simple v, and radius of the circle simple r. And radius of the circle simple r. Derive an expression for capital F. Derive an expression for capital F. Okay. So again start doing this one. Meanwhile, I am also explaining this one, but you can try. So with the limited time that we have, I will also take you through the answer, but try to do this one alone. So as mentioned earlier, the first thing that we have to do is converting this one to an expression. So I can write down force is directly proportional to m to the power x, r to the power y, and v to the power z. So you can put any numerical any algebraic symbols that you like. You can put simple a, b, c, or you can put x, y, z, anything you can put, right? Then you need to convert this one into an equation. Therefore you put a constant k, m to the power x, r to the power y, and v to the power z. As soon as you have written this one, you can write down, you must write down k is a dimensionless constant. It is a must to write this one. Okay, it's a must to write this one. Okay, now what you can do is, now you can write down the dimensions. So here you can separately write down right hand side, left hand side, or you can just write down from this one. So in the previous example, I separately calculated the dimensions. Now in this example, I will directly calculate the dimensions from this expression. So you can put the dimension mark for both sides. So you can put the dimension mark for each term separately, like this way, m to the power x and r to the power y and v to the power z. Now you have to substitute the actual dimensions here. So the dimension of force is m L T minus 2. You can refer and put. K is a dimensionless constant, therefore you better put 1. Capital M is, simple M is mass, therefore put capital M and to the power x. R is the radius, so radius is also a length, therefore you can put L to the power y. And you have velocity, that is Lt minus 1 to the power z. Now you can expand this bracket. So you will get m to the power x, L to the power y, L to the power z, t to the power minus z. Now here also you have L bases, common L bases. Now what you can do is, now you can combine these two. So you can combine and write down m to the power x, L to the power y plus z and t minus z. So you have here m, L, t minus 2. Okay. Now as we done previously, now you have to compare the powers. So you can take one by one. So you can take capital M. The power of capital M in left hand side is 1 and in the right hand side is x. Therefore you can directly write down x is equal to 1. This is your answer. So you better put 2 lines, underline with 2 lines to show that this is an answer. Then you have L. If you equate L terms, powers of L, in left hand side you have only 1 and in the right hand side you have y plus z. So you cannot simplify this one still. Then we have to take the other one also, that is we will take the power of t's also, capital T also. So here you have minus 2 and here you have minus z. So once you remove the minus sign from both sides, you can get z is equal to plus 2. So if z is equal to plus 2, then you can plug the value here. 1 is equal to y plus 2. Therefore you can get here y is equal to minus 1. So now you have already found x, y and z. Now you can rewrite the expression as, right? I will write down the expression here. So f can be written as k times m to the power 1, r to the power minus 1 and v to the power 2. So minus power means you can put it in the denominator. So you can rewrite that expression as, I will erase this part. So f is equal to k times m v squared divided by r. So this is a very clear expression to show the relationship between mass, velocity and radius with force. So you have very clear and a beautiful relationship. Here also the same issue occurs. The issue is you are not able to calculate the value of k by using dimensional analysis. What you can only do is you can build up the relationship, but you cannot calculate the value of k. So that is we call the limitation of dimensional analysis, right? Okay, quickly take this down. Okay, I hope you have already completed this one. Right. Okay, so this is the end of dimensional analysis. So I will give you some exam homeworks to complete. And as I promised the last week, so in the final session of the today's session, we will discuss how to construct graphs as the continuation of last week's basic maths for physics, right? Okay, so you have to put a special star mark down and you can write down this one. So we have to put the limitations of dimensional analysis also. You have to know the limitations, right? Okay, write down limitations of dimensional analysis. Limitations of dimensional analysis. Limitations of dimensional analysis. So the limitations means what are the places where that you cannot use dimensional analysis. That is what we called as the limitations. Okay, first limitation. Dimensional analysis cannot be used to. Dimensional analysis cannot be used to. Dimensional analysis cannot be used to find numerical values of. Cannot be used to find numerical values of proportional constants. Cannot be used to find numerical values of proportional constants. Second limitation, negative positive nature of within brackets sign, SIGN, sign එක plus sign or minus sign කියන එක. Negative positive nature of within brackets sign of proportional constant sign of proportional constant cannot be determined by dimensional analysis. So you cannot say whether that the proportional constant is a positive constant or a negative constant. It is not possible by using dimensional analysis, or you cannot calculate the value of the proportional constant. There is also the limitation. Okay, and the third limitation comes. So now imagine we put powers x, y and z, right? Now there are in complex equations, there are more than 4 powers. That means 4 physical quantities. So if you say force, in the previous one, force was depending on mass, radius and velocity only. These are the only physical properties, physical quantities, right? These were the only physical quantities where the force, the relationship with force. Just imagine there's another one called density or something, rho or something is there, right? So when you have more than 3 terms, x, y, z and something other one, unknown term, then this method is not enough to find the expression. So you have to go for another method. So when you are learning this kind of dimensional analysis in universities, there you learn how to analyze unknowns more than 3. When you have more than 3 unknowns, then you can use that advanced methods to find the values. But up to now, here only 3 unknowns is possible, because we have only M, L and T. So only 3 unknowns we can manage. More than that we cannot manage, right? So you can put the third limitation, rho. Okay, so I hope you all joined the game. Okay, so third limitation I was talking about was when there are more than 3 unknown terms here, 3 unknown powers, x, y, z and some other term, more than 3, then it is difficult to use this method to find the correct expression, because we only have M, L and T terms. That means it is possible to only take 3 simultaneous equations. But when you have 4 unknowns, you need 4 simultaneous equations. So with MLT system you cannot take. So with this method you cannot calculate or you cannot find expressions where you have more than 4 unknowns. So this is a limitation. So you can write down, when there are more than 3 unknowns, when there are more than 3 unknown powers, when there are more than 3 unknown powers, this method cannot be used. This method cannot be used to derive the expressions. This method cannot be used to derive the expressions. This method cannot be used to derive the expressions. So this is another limitation of dimensional analysis. Right, okay. So these are 3 basically the limitations here that we can find, or that we can say about dimensional analysis. Right, okay. So if you need to go for more advanced dimensional analysis, so it is not actually included in A-level syllabus, so it is actually far more advanced. So we actually uses if you have heard matrices, like that way we are using some advanced mathematical methods to find these unknowns, right? So up to now we cannot use these high level mathematics to find the unknowns. So therefore we have to limit that part to only 3 simultaneous equations, right? So these are the limitations of dimensional analysis. Right. I hope this part of the lesson is clear. So if you have any questions to raise, please share in the chat, or you can share the questions to me via the via WhatsApp. Okay. So you can put a message to Nexus group, then they will give you my contact, or you can take from the group also. My contact is there, so you can put me a text if you have any question, or you can put in the chat today, right? Okay, so now we come to the end of the units and dimensions part. So in the next week we have to start the next main topic, that is basically the measurements, right? So measurement is one of the most important thing, because we discussed that anything that can be measurable is called a physical quantity. So we discussed about the physical quantities. Now we have to discuss how to measure them. What are the ways that we have to measure? So what are the things happening when we are measuring something? How a measurement can affect the physical quantity? What happens if we take a wrong measurement? What are the errors associated with the measurement? How to reduce these errors? How to get an accurate answer? So like that we are going to discuss about the measurements in much detail. Okay. So as promised, so I will going to take you quickly through the graphs. Okay. So you can write down in the note, or you can separately write down. There's no issue. But the thing is, you need these techniques, you need these methods for your A-level examination. So you may be writing in 2027, or maybe you are writing in 2028. That doesn't matter. You will need these to your exam. I am guaranteeing that you will have to use these techniques when you are drawing, or when you are selecting an answer for a MCQ in your paper, right? Okay, so please take these notes. This is very serious thing. Okay, so you can write down the topic graphs. Okay, so this is this is not to the lesson, but as a part of basic maths for physics. Okay, right. So graphs we can actually divide into two types. Okay, so the graph, we have linear graphs and we have curved graphs. Those are the two basic graph types. For any of these two graph types, we have common things. So one common thing is, if you need to draw a graph, you should have at least two variables. Without two variables, you cannot draw a graph. So under our A-level syllabus, we are only drawing two-dimensional graphs. That means we only have a two axis, not three axis, only two axis. For three-dimensional graphs, we have to consider three axis. Okay, but A-level only two. So we need two axes. We usually label them as X and Y. Right? Usually label them as X and Y. But what are the real names of these axes? So usually we use this horizontal axis. We call it X axis. That is the usual name. But we call this independent variable. Independent variable. If you don't know, please take a note. Independent variable. What do you mean by independent variable? This is the variable that I can change as I wish. Okay, I can change this value of X as I wish. I can put 1, I can put 2, I can put 3, I can put 1000, like that way. As I wish, I can put any value to X. Right? That is why it is called the independent variable. Because of this independent variable, this Y is changing. So based on the value that we put to X, you can get a value for Y. So this Y value is depending on this X value, right? So we call this axis as, or the y values as dependent variable. Dependent variable. So to draw a graph, actually you must have at least two variables. So one variable is called the independent variable. We usually use that one for x-axis. Other one is the dependent variable. We use that one for our y-axis. Right. That is the first thing that you have to take a note. So quickly draw a small graph like this, and you can label the axis like this. Okay. Next thing is, so the relationship between y and x, we call it a function, right? So relationship between y and x, independent variable and dependent variable, is called a function, right? So we need a function to plot a graph. Without a function, we cannot say how the y value is varied with the x value. Without a function, we cannot say, right? I will explain what is a function. So however, without a function, it is not possible to draw the graph. So you must have a function, right? Okay. Now, as I mentioned earlier, there are basically two types of graphs, that is linear graphs and curved graphs. So we will first consider types of linear graphs. So there are only few types. Other than that, it is not possible to draw linear graphs. So the basic linear graphs, so you can write down the topic as linear graphs. So you have to draw a two axis like this. So that means there's an extension to the minus values also, right? You have extension to minus values also here. So the linear functions, so the linear graphs that we can have is like this way. The equations of linear graphs. So we can have graphs like this. So graph passing through the origin, and it is inclined to the right side of the x-axis. So the type of this graph is called y equals mx. Type of this graph is y equals mx. And we have seen graphs like this. So we can call this graph. So you can see here, this graph is cutting the y-axis from the positive values of y. This graph is cutting the y-axis from the positive value, from a positive value. So we call this graph as y equals mx plus c. So you have already drawn these graphs in your O levels. Okay, this is just a reminder. Then you can have graphs like this, cutting the y-axis from the negative side. So you can write them as y equals mx minus c. And you have graphs which are inclined to the other side, like this way. So this is called, if it is inclined to the left hand side, definitely it should be minus mx. It should be minus mx. It is passing through the origin, therefore no any other terms here, just y equals minus mx. If this graph is cutting the y-axis from a positive value, then this is y equals minus mx plus c. This is minus y equals minus mx plus c. Then the other one, like that way, this is y equals minus mx minus c. Right. These are the basic ones. Okay. So we have another few. We can draw linear graphs. So something like this we can draw. A vertical line. So a vertical line represents that the x value of this one is not changing with y value, right? The x value is fixed for a vertical line. Therefore, we call this x equal positive constant graph, x equal plus k. If you find a vertical line here in the negative side, we call this y equals minus constant. Similarly, you can have this kind of lines, horizontal lines. So in horizontal lines, y value is not changing throughout the line. Therefore, this is y equal plus k graph. And you can have constant lines in the negative side. You call it y equals minus constant. So if you consider this whole syllabus for the whole world, these are the only graphs, only linear graphs that are possible. There is no any other graph in the world which is out of these formats. All the graphs are included here. All the linear graphs are included here. No any other graphical format, linear graph other than this. Any linear graph must be in one of these formats. So you have here 10 formats, no? 6, 3, 3, 6, 6 and 4, that is 10. So only these 10 lines are possible in the graph, right? If you can draw any other line, I say it is impossible. You cannot draw any linear line out of these equations or these formats. Not possible. Right. Then we will go to the curves. So hope this is very clear. Please draw this one. Okay. Then let's go to the curved graphs. This is not much difficult from the Animal AC. Not difficult. So then keep in mind. Now if you go to the curved graphs, this is y, this is x. So what are the possible graphs is, we have learned something like this parabolic shape. We have learned, no? This is y equals x squared, and you have the negative parabolic shape like that way. You call it y equals minus x squared. And if you go like this, this is y equals x squared plus c value. And if it goes like this, the shape is y equals minus x squared minus c. Okay, so like that way you can draw multiple, you can draw something from here and you can write down y equals x squared minus c. That also you can draw like that way. So not that much is required, but keep in mind, when you have a higher power of x, then you will have a curved graph, not a linear graph. Okay, for all the higher powers of x, you will get a curved graph, not a linear graph. Right. Quickly draw this one also. Okay, the next one is the most important one. Okay, so you have to keep this one, or you have to understand this one very clearly. Right. So there are a lot of graphs in physics that we will come across in this format. Y equals 1 over x format. Y equals 1 over x format. So y equal 1 over x means that the independent variable and dependent variable are inversely proportional, right? So this one is in the top side, x is in the, this is in numerator and this is in denominator. That means they are inversely proportional. So this is something like this, 1 over x. So when you have an inversely proportional graph, this is how to construct this one. This is very, very important. Okay, very important. This is the most frequent graph that we find in A levels. Right? You must know how to draw this one. Right? So when you are drawing this one, you have to consider plus values and minus values. Right? Okay. So now if you take this expression y equals 1 over x, we can check few values before drawing the graph. So these values are, we can check what happens to y if x goes to plus 0. That means, what do you mean by plus 0? Value of x is 0 at this point. Right? So plus 0 means a value just before 0 but in the positive side. I am putting plus 0 to represent that I am considering a value very much close to 0 but from the positive side. So if you put x equal plus 0, your y value must be 1 over 0. Right? If you put x equal to plus 0, then your y value not actually equal. We will put an arrow to show that it is not equal but it is reaching to this value. When x is reaching to 0 from positive side, that is the meaning. Y is moving to, or y is reaching to 1 over 0. If anyone can remember what is the value of 1 over 0, I explained I think the last week also 1 over 0, right? 1 over 0 is infinity. 1 over 0 means infinity. So here plus infinity because we have plus 0. So how do we represent a line going to infinity? Okay, so the meaning of this one is when x value is reaching to 0 from the positive side, y value is going to the plus infinity. So y plus values of y is in this side, negative values of y is in this side. Therefore, it should go to plus infinity. So it should go up in this direction. But can we draw any line to the infinity? Can we draw a line to infinity? No, it is not possible to draw a line to infinity. Right? So what the technique that we used is, we are drawing a small parallel line to the y-axis. We are drawing a small parallel line to y-axis. That is to show that the y value is going to plus 0. Then what we do is, next one is, we are sending the x value to minus 0. We are sending the x value to minus 0. That means we are sending the value, or we are reaching the 0 from negative side. We are coming from this side. So then what we get is y goes to minus 1 over 0, because I am putting a minus sign here. When it is minus 1 over 0, you will get minus infinity. So how do you represent minus infinity? When you are coming from this side, y goes to plus infinity. When you are going from this side, y goes to negative infinity. Negative infinity is located in the bottom. So you can draw a parallel line here, a small parallel line here. You have to draw a parallel line here, parallel line to the y-axis. Similarly, now you can do the other way around. That means you can send x to plus infinity and check where the y goes. X going to plus infinity means you are going to this side. So when you go to plus infinity, you will get 1 over infinity, right? You will get 1 over infinity. So last week we discussed 1 divided by infinity is equal to 0. As we are getting plus infinity, your answer also plus 0. That means when you are going to the plus infinity, y value is coming to positive 0. So positive 0 means just above 0. So but to reach positive 0, you have to go to the infinity, x infinity. So to show that x is going to infinity, you put a parallel line piece parallel to the x-axis in the end of the axis. We are putting a small piece of line at the end of x-axis to show that x is going to plus infinity. And here also you can now put x goes to minus infinity, then you will have 1 divided by minus infinity. So 1 divided by minus infinity means minus 0. So minus 0 means you are going to the minus side of x, going to the minus infinity, then your y value goes to minus 0. Minus 0 means just below 0. So x is going to infinity, then y is coming to 0. Therefore, to show that x is going to minus infinity, you have to draw a small piece of line like this. So now you have to combine these lines. So you have to combine this line and this line. There's only one way to combine these two lines. That one way is you take this one down and you curve it like this and you connect it. Similarly, there's only one way to connect these two lines, that is by taking and curving like this. Right. So we call this kind of variations, drawing a line parallel to the axis, we call it asymptotic. Asymptotic curves. These are very much frequent in physics. Okay, you will always find asymptotic or asymptotic curves in most of the lessons. Almost all of the lessons you can find this type of graphs. Right? This is very important to understand how to draw this one, how to get this one. So if you have anywhere where you have a inversely proportional relationship between independent variable and dependent variable, then you will definitely get a curve like this. Right? If you have a minus value, let me draw here or here. If you have minus 1 over x, then what will happen is your graph will turn to the negative side. That means this is the positive graph, so the negative graph become like this. So you can draw the same diagram, but please use a different color. First draw small parallel lines at these places and you connect them. So the green line is representing when y equals minus 1 over x. It will be like this. When y equals 1 over plus 1 over x, then the graph will be like this. Right? In gravitational fields, in electric fields, so you have to draw numerous such kind of graphs. So therefore it is very, very important to understand how to draw these graphs. Okay. So this is the end of the basic maths for physics part also. So now we have discussed almost all the necessary maths parts, and we have discussed physical quantities and dimensions part. Okay, so the next day we have to start the measurements. So on Thursday we will start the part measurements, and they are, as I mentioned earlier, we will learn what are the measuring instruments that we have, what do you mean by a measurement, what are the errors when we can have when we are taking a measurement, and how to mitigate those errors. So these parts will be discussed on Thursday. Right. So if you have any question, please do not hesitate to ask. You can put in the chat, as well as you can text me. And today we will not have much time to do homework. So we will do homeworks on Thursday. I will give some homeworks on Thursday. So but please go through the examples that we have done here. It is very important that you recap every day. So please go through and please come prepared to the next class, so we can go quickly with the theory part and we can do a lot of questions later on if we complete the theory parts as much as quickly. Okay. So thank you very much for joining with Nexus 12 program, and I hope you learned something today, and we will learn more every day in this 1 year period. So thank you very much, and have a nice day. Thank you. Good night.